It's my pleasure to be co-chairing the session today on stratification and individualization in the system of radiation protection with Tatsu Imaoka. And we share the pleasure of being on Task Group 111, one of ICRP's activities in this area, looking at the basic science behind variation in response between individuals. So the format of this session is broadly similar to the others you've had so far. We're going to have a summary of poster and other presentations from Launa Hafner in a moment, followed by 4 talks, one from Wei-Sen Chang, then Tatsu Imaoka, my co-chair, Colin Martin, who's at the far end, finally with Richard Wakeford. So without further ado, I'll hand over to Launa to summarize the poster presentations, please. Thank you, Launa.
So, welcome to this session of stratification and individualization. I'm going to summarize the contributed posters to this session. There have been 4 posters submitted, so we'll have time to briefly go through all the posters. The first poster comes from Seong Kim from South Korea et al. It's called Advancing Individualized Radiation Dosimetry, Establishing Comprehensive Phantom Libraries Based on MRCPs. So in this study, the high deformability of mesh phantoms is used to establish a set of arms-down body size-dependent adult and pediatric phantom library based on the new developed mesh-type reference computational phantoms for reliable dose estimation to individuals. Additionally, also arms raised and arms removed phantom libraries were developed for the use in CT dose evaluations. In total, 824 phantoms covering a wide range of heights and weights were developed. Further, the impact of the body sizes and the arms on dose calculation were investigated. Therefore, the phantoms were implemented in the Xeon 4 Monte Carlo radiation transport code to calculate organ doses for 2 cases. For the first case, it's for external broad parallel photon beam in anterior-posterior direction. Here, the dose for the abdominal organs of the phantoms with more body fat showed smaller values than those of the skinny phantoms at low energies due to the shielding effect of the body fat, and vice versa at high energies due to the establishment of photon buildup region. In the second case, for helical chest CT examination, the arms removed phantoms showed the highest dose values and the arms down phantoms showed the lowest dose values due to the shielding effect of the arms and shoulders. The researchers conclude that the developed phantom libraries are expected to improve the accuracy of dose estimation to individuals by properly considering the body size and arms of the individuals. The second poster comes from Masanori Tomita and Junja Kobayashi from Japan. It's called Individual Differences in Sensitivity to Ionizing Radiation Depends on Dose Rate and DNA Repair Capacity. The aim of this study was to investigate radiosensitivity under low-dose rate irradiation condition. And in the study, cell survivals of 2 radiosensitive normal fibroblasts, 2 normal fibroblasts with normal radiosensitivity, and normal human fibroblasts WI38 cells were found to not decrease significantly after 2 weeks of continuous irradiation with low-dose rate gamma ray at 1 milligram per hour with a cumulative dose of 0.34 gray. At a dose rate of 50 milligram per hour, cell survivals of 2 radiosensitive normal fibroblasts were found to be lower than those of the other cell lines. Additionally, the expression levels of some homologous recombination-related genes of 2 radiosensitive normal fibroblasts were found to be significantly lower than those of the other cell lines. And the individual differences in radiosensitivity were found to vary with dose rate according to the expression levels of DNA double-strand break repair-related genes, but the differences, if any, were found to be very small at low dose rates. Finally, the role of homologous recombination is also found to be important in the case of prolonged exposure at higher dose rates, and the researchers conclude that in a future system of radiation protection, it will be more important to assess risk by dose rate at the time of exposure rather than by accumulated dose. The third poster comes from Alem Chouini from Qatar et al. It's called Established Facilities DRLs based on clinical indication and BMI categories for CT scan. The aim here was to regroup most factors affecting radiation dose in CT scan examination to establish diagnostic reference levels to enhance the sensitivity of dose monitoring software and to improve the justification process. Therefore, CT scans were classified into 5 different BMI categories based on clinical indication, and about 1,743 exams from 2 different CT models were retrospectively collected and analyzed. 20 cases were collected per BMI, per CT unit, and per clinical indication. So taking normal BMI as a reference, the CTDI volume values were increased as the body mass index increased. So the researchers found that overweight patients required about 40% more dose compared to normal weight patients, while obese classes 1 to 2 had about twice the dose. They state that comparing each category of BMI to specific dose reference level estimated, the dose can be adjusted to improve the image quality, especially for the obese patient, while require a higher dose to reduce the noise and to improve the justification process. Also, the 50th percentile values are presented for the CTDI volume and the DLP for each of the 5 CT exams for different BMI categories and different CT scanner models. They conclude that a new classification scheme considering BMI, clinical indication, and CT scan models provides a tool to perceive differences in dose metrics among patient size on CT body exams. And the last contribution to this session comes from Julie Leblanc from Canada et al. It's called How Does Biological Sex Modify the Risk of Ionizing Radiation-Induced Health Effects? Here the aim was to evaluate the current evidence for a systematic review of how sex modifies the risk of ionizing radiation-induced health effects. Therefore, cancer and non-cancer effects were analyzed. In the first phase of the study, independent abstract and title screening using the Distiller SR software with assistance of the AI screening function was performed, and consensus over study relevancy was found. In the second phase, an independent full-text screening was performed, and consensus over study inclusion was found. And currently, quality control of data is being conducted for the human category, and further refinement is done of the human studies by removing outdated cohorts. So thank you, and don't forget to check all the posters out. They're accessible on the ICRP online poster platform. Thank you.
Okay, so let's now move on to the first presentation, which is given by Dr. Wei-Shan Chan from Tokyo Metropolitan University. So the floor is yours.
Okay, thank you for your kind introduction. I'm very honored to have this chance to share my research related to CT exposure based on age and BMI here. Before I start the presentation, I have to say that I actually misunderstood the presentation time, so I will speak a little bit faster to make it. Yeah. Okay, so here is the outline for today. I will introduce current situation of medical exposure from CT and the previous studies on the relationship between medical exposure and risk of cancer. After that, I will introduce calculation by CT dosimetry and the individual difference in CT exposure based on age and BMI, and make a quick conclusion. So as you may know, that medical exposure has been the largest source of radiation of population other than the natural radiation. And we can see the figure here is the annual effect dose from different unscared medical exposure evaluation. And there is an increase trend until last version published by 2020. But the difference is, however, just within the bound of the estimated uncertainty. So the content of the medical exposure, we can see from the left figure here, that it says CT contributes more than 60% of the effective dose in medical exposure. And in contrast, in Japan, according to the last version of Japanese national dose, it says that a new effective dose from medical exposure is like 2.6 millisievert, and the CT contributes like 70% of it, which sounds very high, but actually it decreased from 3.8 millisievert to 2.6 millisievert in 10 years. And also we have to notice that Japan is an aging society, and normally the frequency of CT examination is proportional to the age. So there have several previous studies examined the relationship between medical exposure, or technically CT, and the risk of cancer. For example, the Brenner, they found that the estimated lifetime increase in the cancer modality risk attributable to the relationship or radiation exposure from a CT scan in a 1-year-old are like 0.18% for a donor. And also in Pierce, Matthews, and Huang's research, they also found that for children who had received CT had the cancer are found to have cancer with a large probability. So so far, I think we all recognize that there is actually a gap between the CT dosimetry metrics and what we really want to know, because the traditional CT dosimetry metrics like CDDM, DLP, and SSD, there are list index are sufficient for the purpose of such as like collection data for patient dose or setting DRL. But what we really want to know is about the risk. And we know that there are variations in risk to different organs. For example, the bone marrow column, they have higher cancer risk, and for the brain, they have lower cancer risk. So it is favorable to be able to estimate the organ dose. And there are actually several methods to estimate the organ dose, and the most straightforward and easily to adopt method is SSD-based organ dose, using SSD to estimate the organ dose. However, there are many uncertainties are included in this method. For example, if we use a geometry-based SSD to estimate the organ dose, we might have an uncertainty up to 20%. And there are many other uncertainties are actually summarized in the AIPM report 246. So if you feel interesting, maybe you can go check that for more detail. And in addition to the uncertainty, we also have to know that there are many actually limitations in this method. For example, the SSD is not actually suitable for estimate the dose from partial organ irradiation. So to have a more accurate organ dose estimation, I will going to introduce the calculation-based CT dosimetry. Well, no, and it's usually also called the Monte Carlo-based CT dosimetry. This method can provide a more accurate estimation, but it is quite complicated. That to implement this method, we need to model the X-ray source and to do a lot of measurement to get the spectrum, bow-tie filter shape, and geometry, anything from the X-ray source. And in addition to the modeling, we also have to prepare the model of patient's anatomy. Some methods can use MIRD phantoms, some use the voxel phantoms. And after preparing these two things, we also need a description of the scan parameter, which is for sure, and also a mechanism to transport photons through the geometry and tally those to the organ of interest. So here I'm going to introduce a Monte Carlo-based CD dose calculator named Wazali. I'm going to introduce this tool not only just because I do my research using this tool, but also because it is free. So after this simple theme, if you feel interested and want to do research related to CD, you may just take a registration and use it anyway. And what Wazali is a web-based open system. It offers like CD dose calculation for 18 phantoms, like 5 different age children phantoms for boys and girls, and also for body shape for adult phantoms. And there are 52 scanner modes are included. And also, in addition to the regular constant irradiation condition, they also offer a calculation mode to. They are also available to do those calculations for auto exposure control, and also they recently have support the SSD corrected organ dose, which I will actually introduce later. And here is a graph showing the comparison of the organ dose between different body shapes and calculated by Wazali. And you can see that the horizontal axis is just the organ, and the perpendicular axis is the absorbed dose, and the orange is the thin people, and the blue is the standard normal body shape people, and the gray is fat. Yellow is like obese. And we can find that almost for the organ, the thin people receive the highest absorbed dose. This is because the large people, they have more fat around their body, which is the fat can become a shielding material for the internal organ. But that's why the thin people will receive higher absorbed dose. In contrast, we usually have a large tube current when we take X-ray for large people, because the large body will have a poor image quality. So it's kind of like a trade-off things. And here is a quick brief summary of what I just presented before, and I will just skip it. So going to the individual difference in CD exposure. In my research, the correction method I used for BMI is sorry. There is previous studies found that there are a good correlation between the effective diameter of body and the BMI, and the Ornell's group, they proposed equations to calculate the effective diameter using BMI like this, a linear equations. And for the age, what I used is the equation derived by APM using the phantom in ICRU 74, which is like this. So in my research, what I used is Wazali, of course, and in addition to the calculation, I also do some measurement using radiophoton luminescence glass dosimeter and the atom series phantom. Because for the phantom in Wazali and also the atom phantom, we can know the weight, height, and of course BMI for this phantom, so it is easy to do the evaluation for BMI correction. And of course, I also use the SSD conversion factors from APM. The irradiation condition was just shown on this table. The scan length was shown on the upper figure, and the setup was just like the lower figure here. So here is the result for the BMI comparison, and we can see the horizontal line axis is indicated the organ, and the black bar is the calculation result by Wazali, and the white bar is the measurement result by glass dosimeter. And I took a ratio between the calculation and the measurement result, which was indicated the circle here. And also the dot line here is the SSDE conversion factor. So we can see that most the ratio of Wazali and glass dosimeter, they agrees well with the SSDE conversion factor. But some organ shows like breast or bladder, they are a little bit higher compared to the conversion factor. So I make a graph for each organ and to see the relationship between the BMI and the organ dose. Here we can find, and also the rate circle here is the measured result, and we can find that for many organs, the rate measured result agreed with are very close to the calculation result, and most organ dose decrease with increasing BMI. But we found that the relationship between BMI and the organ dose are not linear. So if we want to use BMI to estimate the dose, maybe it is not to use only a linear function, but also we have to use interpolation will be more suitable. And for the age-based, here we can see that the left figure is the result for Wazali, and the right figure is the result for glass dosimeter. Black bar for both are the result for 10-year-old boys, and the white bar are the results for 5-year-old boys. And it's the same. The ratio the circle indicates the ratio of these two ages organs dose, and we can see that the conversion factor based SSDE was 0.889 here, which is also very close to our results for both calculation results and measure results. Okay, that's my presentation for today. And today I gave you an overview of current situation of medical exposure from CT and CT-related dosimetric. I also introduced some of them, and I also introduced the implementation of SSD associated correction factor to CT dosimetry system is feasible, and that organ dose estimation accuracy can be improved by the correction method based on age and BMI. Thanks.
Thank you, Wei-Shen. And because we have a discussion time later, let's move on to next.
Yeah, thank you very much, Wei-Shen, as well. Yeah, just to remind everyone, there should be a discussion and question and answer session at the end, so we can move on to our next presentation, which is from Tatsuhiko Imaoka from QST here in Japan, who'll be talking about some review work he's been doing under the, largely under the sort of ICRP Task Group 111 work, looking at animal studies and how they provide insights on individualization of cancer risk. Thank you, Tatsu.
Okay, good afternoon. So I'm going to talk about the individualized radiation cancer risk insights from animal studies. So as you may know, cancer risk is influenced by age and sex, as well as various environmental factors and genetic factors. And although epidemiology is a very important source of knowledge, animal studies are also important in that they complement epidemiology by identifying priority areas of research and also by adding cross-species information and also mechanistic viewpoints. So today's talk will include my task group 111 work, which is a review on the evidence for modifiers of cancer risk from animal models. And in the latter part of my talk, I'm going to talk about the possibility of extrapolating radiation cancer risk from animals to human, which is work performed by Planet, which is a platform for all those radiation research in Japan. Okay, so the first part, I'm going to introduce our work on the systematic review on the evidence of modifiers of cancer in the animal models. So this is the overview of the method of the systematic review. So we, in the TG meeting, we made an agreement on the selection of modifying factors, and which are 18, including age, sex, smoking, etc. And after that, we performed PubMed searches with specific sets of words, and the example for the words are indicated here. And through this, we got more than 2,000 potentially relevant papers. And after screening of their titles and abstracts, we had narrowed them down to over 400 papers, which are clearly or possibly relevant. And full text analysis was done for these papers, and we got 352 papers and we did perform the evaluation on these papers upon indicated criteria. So I'm going to briefly show you the conclusions of this systematic review. So first, regarding age and sex, we had found 80 papers. And regarding also the cancers, a younger age at exposure and female sex are associated with a higher risk. And prenatal exposure imposes smaller risk. And this is an example of a mice experiment which shows the high susceptibility during neonatal and juvenile period. And this is a 6 ratio for all tumors, indicating that females are more susceptible. And for such specific cancers, younger age at exposure is generally associated with high risk, but there are variation between the sites. And regarding breast, in females, the peripivotal period is the most sensitive. The effect of sex also varies by site. And regarding leukemia, risk peaks at young adults and is higher in males, as shown in the graph here. And second is the lifestyle factors. We found 38 papers for this category. And regarding smoking, there was a study indicating that the interaction of the plutonium dioxide aerosol and cigarette smoke on induction of lung cancer are significantly larger than additivity. And in this study, they use this kind of risk model to indicate that the interaction is greater than additive. And regarding the body weight, diet-induced weight gain, either through overall food intake, carbohydrate intake, or fat intake, is associated with increased solid cancers and leukemia. And this is the example. And pregnancy and hormones modulate radiation-induced breast cancer and also strontium-induced bone cancer. And the third category is underlying conditions. And the fourth category is other environmental factors. We found 88 papers in total for these. And for the underlying conditions, chronic inflammation increases radiation-induced tumors. And this is an example of a mouse experiment on the leukemia incidence, in which radiation and inflammation seems to interact synergistically. And regarding UV and sunlight, there are only limited evidence which suggested additivity or interaction regarding radiation-induced skin cancer. And co-exposure to chemicals is often additive to radiation-induced cancer, in a meaning that the exposure to chemicals further increase the incidence or mortality from cancer. And there are some quantitative analysis on the interaction which suggested either additivity or multiplicativity. And this is an example that shows a multiplicative interaction by using this risk model. And radioprotectors, free radical scavengers, and some food ingredients are shown to reduce radiation-related cancer risk. And this is an example for tempo inhibiting the incidence of leukemia in mice. And the last category is genetics and epigenetics. So strain of the mice and rats and germline mutations related to human cancer syndromes and DNA repair affect radiation-related cancer risk. So this is an example showing that the strain of the mice very strongly influence the incidence of liver tumors, which was induced by neutrons. And this, the center one is the graph of lifetime of mice, wild-type mice, and p53 heterozygous mice, which also indicates the additive effect, seemingly additive effect of p53. And the right one is the BRCA1 knockout model, and in which the orange one is the wild type, and the blue one is the knockout rat, indicating susceptibility to radiation in this model. And there are very few papers on the epigenetics. So I'm going to add a few words for BRCA1 knockout rat. BRCA1 and BRCA2 genes are involved in homologous recombination repair, and their germline mutations cause hereditary breast and ovarian cancer syndrome. And epidemiology, some epidemiology suggests an elevated risk of breast cancer in BRCA1 and 2 mutation carriers after receiving diagnostic radiation at a young age. So we generated a rat strain harboring a human-relevant BRCA1 variant by gene editing. And these rats, these heterozygous rats, develop breast cancer at a higher rate than BRCA1 plus rats after single prepivotal radiation at 2 grades of gamma rays. And the induced tumors retain the BRCA1 wild-type allele, and exome sequencing is now underway to delineate the mechanism of cancer, which was presented at the JRRS meeting upstairs. And induction and the repair B53BP1 force in these rats are now also under investigation, supporting no obvious impact of first component of DNA repair, but there are some indication of difference in the later component of DNA repair, which was also presented upstairs yesterday. So the second part of my talk is human mouse comparison of radiation carcinogenesis, because we had now the animal evidence, but currently we do not have a concrete method to extrapolate the information from animal studies to assessing human radiation risk. So we tried that issue in this work. So mouse models are vital for assessing the risk from radiation, but the difference in the dose response between humans and mice precludes direct application of experimental evidence to humans. So the objective of the study is to delineate the mechanism underlying the human-mouse difference in radiation-related cancer risk based on the mathematical concept of multi-stage carcinogenesis. In multi-stage carcinogenesis, you assume that you have many normal cells, and from which at a certain rate, you have cells with one mutation, one driver mutation. And from this population of cells, you have, at a rate, you have cells with two mutations. And repeating this, you finally have a cancer cell. And this is the multi-stage carcinogenesis model. And to link this model to the real-world data of the cancer mortality rate, we assumed a latency period between the emergence of a cancer cell and the occurrence of death from cancer. And without radiation exposure, you only have spontaneous mutations. And to make a long story short, you by resolving array of equations, you get this one, which predicts that the cancer rate is a function of the power function of the time or age. So the incidence increases as the age increases. And if you assume that radiation induces mutations only during the period of exposure, which is from time E1 to time E2, then you have this equation, which means that there should be some shift in time in the age, in the rate of cancer. So now we fitted this model to the atomic bomb survival data published by Dr. Ozasa in 2012. And this graph shows the relationship between the dose and the shift of cancer rate in time, which was expressed by this equation. And we found that in humans, 1 gray of radiation shortens the time to cancer by 7.8 years. And in mice, similarly, 1 gray of radiation shortens the time to cancer by 0.049 years. So obviously, the lifetime of these species are different, and the effect of radiation was also different, and there was roughly 100-fold difference between these species. And we next attempted to understand this difference in a quantitative manner. So, and because the time shift is expressed by the ratio of the radiation-induced and spontaneous mutation rates, we looked into the literature for these values. And regarding the radiation-related mutation rate, there are many papers on the HPRT mutation frequency in human and mouse cells, and these data indicated that there are virtually no species difference. And regarding the spontaneous mutation rate, in the literature, it was obvious that there was nearly a 100-fold difference in the spontaneous mutation rate per year. So we found that there was 100-fold difference between human and mouse, and this difference, the difference in cancer mortality, is dictated by the difference in the mutation rates of these species. So to conclude, animal studies support that young age at exposure and female sex confer high radiation risk of solid cancer, and male sex for leukemia, providing findings consistent with epidemiology. And animal studies suggest significant interaction between radiation and various lifestyle, environmental, and genetic factors on cancer risk, supporting a need for further research in humans. And the observed human-mouse difference in radiation cancer risk may be mostly explained by the nearly equivalent sensitivity radiation-induced mutagenesis and nearly a 100-fold difference in the rate of spontaneous somatic mutations. And I'd like to thank the members of QST, ICRP task group, and Planet, and also the part of the study was supported by the Ministry of the Environment, Japan, and JSPS in Japan. Thank you very much for the attention.
Thank you, Tatsu, very much for that very insightful talk, and I'm sure there'll be some questions later on. I'll hand you over to Colin.
Yes. So our third speaker is Colin Martin, and from University of Glasgow, United Kingdom. So please.
Oh, good afternoon. I'd like to try and put the case for why I think individualization of very logical protection in medicine should be used. So I'll talk about individualized medicine, use of effective dose, variations in risk with age and sex, the dependence of dose on body size, size-specific effective dose, possibly the use of size-specific dose estimate, and stratification of dose-related detriment for medical patients. So personalized medicine takes the form of implementation of individualized diagnostic and therapeutic strategies. So the idea began after the Human Genome Project in about 2004. So this is linked to changes also in healthcare systems and societal values. So each person's health and clinical needs depend on their individual heredity, their health-related behaviors, and their metabolism. So treatments and drugs are often prescribed for a particular disease without much consideration of the makeup of individual patients. So many medications are effective for the majority of the population, but they may not benefit all individuals, and they may induce adverse side effects in some. So personalized medicine involves the identification of subgroups and stratification of the patient population to improve treatments and reduce risks. So looking at the treatment of cancer, the genomic information about tumors can lead to better treatment strategies. The drugs that fight cancer have different mechanisms. They do it in different ways, and appropriate ones tailored to the genetics of individual patients' tumors can be selected. So patient populations may be divided into clinically relevant subgroups for use of such custom-made therapies. And then again, in radiotherapy, the risk of tissue reactions in normal tissues places limitations on the therapeutic dose that can be used to kill tumors. So genetic conditions, as we've heard today, place some people at higher risk of tissue reactions following radiation exposure. So if in the future radiosensitive individuals could be identified through an assay of gene expression, their radiotherapy treatments could be modified accordingly. But radiotherapy is at one end of the spectrum of medical exposures. Much larger numbers of patients are exposed to lower levels of radiation from medical imaging. And for this group, really the only risk-related quantity available is effective dose. So effective dose is used routinely in medicine to give an indication of doses from imaging procedures. And in fact, the availability of a single dose quantity has helped to educate the medical community about the relative dose levels from different types of examination. And patients who are re-examined many times by CT can receive effective doses of hundreds of millisieverts. Now, the concept of effective dose was developed as a measure of radiation exposure relating to the risk of stochastic effects. It was designed to be used for planning radiation exposures and monitoring doses, and it's proved very successful as a measure of occupational and public exposures. But this risk is averaged over the whole population and takes no account of differences in age and sex. So organ doses are derived for a person of average build. So effective dose was not designed to capture potential harm to individual patients, so we can't really use it for individual patients. What we need is an individualized dose quantity for this. Now, considering for a moment the variations in risk with age and sex, I'm sure we're all familiar with graphs of this type, where the risk gradually declines with age, so that young persons are at greater risk, and there's a distinct difference between the sexes. So since the creation of effective dose, knowledge of risks from radiation has expanded more and more based on epidemiological studies. So we can draw distinctions in the risk from extensively similar exposures to different individuals. And we now are in certain places starting to track cumulative effective dose. But if you take this over time, over a person's lifetime, really it's got little value as the risks gradually change with time. So if we're going to do this, we need a different dose quantity. Now, you can calculate risks of cancer from coefficients that we had in publication 147. This contains tables of factors giving the risk of cancer incidence per unit effective dose by age and sex for a range of X-ray examinations. And these are quite useful. They can be used to calculate risks of stochastic effects adjusted for age and sex for patients who receive cumulative effective doses over 20 millisieverts. But if we look at the upper and lower ends of those, in fact, those sort of factors can be 20 to 100 between children and older age groups. So I want to briefly describe an analysis of risks from cumulative CT scan doses. We carried out a study of 105,000 patients undergoing CT scans in the UK over a period of 5.5 years. We summed all those doses, and we found that 17,726 patients received effective doses between 20 millisieverts and 470 millisieverts from CT examinations of the trunk. Now, we derived that using the sort of radiometrics dose management software. So this uses phantoms, some of the stylized phantoms that you've seen in an earlier presentation, to derive values for the doses to all the individual organs, and then sums those with the weighting factors to derive the effective dose. So that we could then calculate risks from the effective dose values using the age and sex risk coefficients from ICRP 147. So this is a sort of graph. If you put all the points on, they sort of blot, you've got thousands of points which blot out the whole graph. So what I've done is put in the median value, the 25th and the 75th percentile, and the 5% and the 95% percentile. And you can see there's quite a big variation in the excess lifetime cancer incidence per 1,000 persons when plotted against this cumulative effective dose. So a patient receiving an effective dose of 200 millisieverts could have a risk of this initiating a cancer anywhere between 1 in 1,000 and 1 in 70. Admittedly, you might have some indication of that from their age, but it shows the big variation that we have in risks and the reason we can't use this for individual patients. And then we've talked, earlier speakers have talked about the use of reference phantoms. So for occupational and public exposures, individual doses can seldom be evaluated accurately because of the limited information on their positions and the varied radiation fields. So the reference phantoms in ICRP 110 and 145 are used for planning and monitoring of exposures. But for most medical exposures, the radiation fields are known with quite reasonable accuracy, certainly a lot better accuracy than the occupational ones. And so organ and effective doses are can be calculated from measured quantities for medical exposures using coefficients derived from Monte Carlo simulations because we've got a much better handle on that dose distribution. So organ doses for individual patients vary with their stature, but this is not taken into account because we're using the reference phantoms. Again, this was being touched on earlier. So we can now have libraries of anatomical phantoms, and there are a number of different research groups who have developed software for calculating organ and tissue doses based on these libraries of anatomical phantoms of varying size. So suitable phantoms can be selected to reflect the stature of individual patients, and these can be used with dose management software systems to improve assessment of doses to organs and tissues for individual patients in CT. So use of more accurate organ doses can improve the assessment of individual patient risks. So I often use a size-specific value of effective dose derived by combining the modeled organ and tissue doses using the ICRP tissue weighting factors. So this is not effective dose, it's a modification, it's a size-specific or patient-specific value. So if we look at the variation in size-specific effective dose with trunk diameter. So one of my colleagues has carried out a lot of simulations using Monte Carlo on a whole range of different phantoms. But what I've selected is 32 adult phantoms, all with the same height, 1.7 meters. So you're looking at the same organs within that part of the body, and calculating the size-specific effective dose for a particular chest, abdomen, pelvis CT scan with a particular CTDI vol and dose length product and scan length. So the size-specific effective dose for a given CT scan declines with trunk diameter because there's less tissue attenuating the incident X-rays. And in fact, stature can give variations in dose and risk of up to 60%. So that's another factor to add into the uncertainty when we're looking at individuals. So CT scans make up over 60%, as we've heard today, maybe 60% or even 70% of the cumulative effective doses from imaging. So organ doses from CT scans can be derived for phantoms matched to patient size and used to calculate a size-specific effective dose. The Monte Carlo simulation methods also have the potential to calculate organ doses directly from data on organs lying within CT scan images. And my Chinese colleague on Committee 3 tells me his group can now do that within 2 seconds. So this is likely to be possible within short timescales in the future as the speed of these processes is improved. So the possibilities of improving organ dose assessment for other modalities is likely to improve as well. So looking at individualized dosimetry, improved organ doses can be derived based on patient stature rather than reference phantoms. There's good evidence about relative risk for development of cancer based on age and sex. Data could be used in developing a new quantity to describe risk to individual patients, and this would be in line with the individualization and stratification in other areas of medicine. So such a quantity could improve the medical community's understanding of risks from imaging and clarify the variations with age and sex by trying to create a sort of single quantity that we can use. It would allow meaningful values of cumulative dose linked to risk for an individual to be derived. So in summary, personalized medicine takes the form of individualized diagnostic and therapeutic strategies. Effective dose has been useful in educating the medical community about patient doses. Patient stature can give variations in organ doses and risks of up to 60%. And organ doses could be derived for phantoms matched to patient size, and in the future, organ doses could be calculated directly from CT scan images. So risks to individual patients vary by factors of 10 to 15 or more, so due to these differences in age and sex. So age and sex adjusted factors could be applied to organ doses to create a new detriment quantity for individuals. And lots of research centers are looking into these sorts of ideas. And if ICRP doesn't come up with a lead on the approach that should be adopted, there's a danger of things going off in all different directions with a multiplicity of methods, which would not be a good thing. So such a quantity could improve the medical community's understanding of risks and will be in line with individualization in other areas of medicine. I'd like to acknowledge my colleagues, Michael Barnard in Oxford for helping with the collection of patient scan data, Abdullah Abu Hamed in Saudi Arabia for the Monte Carlo simulations. And thank you for your attention.
Thank you, Dr. Martin. Okay,
So the final speaker of this session, is Richard Wakeford from the University of Manchester in the UK, and he'll be talking a little bit more about doses and risks in medical exams and the impact of age and sex.
Okay, right. My talk, as Simon says, is about the impact of age and sex, medical exposures, and my co-author is John Harrison, who was the principal author of publication 147, and we'll be looking at that in some detail on this. So back to basics, really. Publication 103, the recommendations of the ICRP. It's the system that is intended to be applied globally. It's a global system. It's scientifically based. It's conservative, but not too much so, and it's practical. I mean, that's the whole point of the system, such that it works. But if you go back to what was done, basically, the technical basis of publication 103, then it starts out with sets of excess relative risk and excess absolute risk models, 10 specific organs or tissues, and a group of remaining solid cancers. And that comes from the atomic bomb survivor instance data as was available at that time. And of course, we're going back a bit now. And importantly, those models allowed for risk variation with sex and age. And what Publication 103 does is to aim to this, this globally applied system. First of all, it age averaged the lifetime cancer risk was computed for two composite populations, a Euro-American population and an Asian population, using these excess relative risk and excess absolute risk models. And then more averaging was applied, weighted averaging of these two model estimates. I'm certainly not going to go into any details. The DDREF2 apply for solid cancers, and further averaging over sex and population. And what you get at the other end of this is the nominal risk coefficients, which is the average lifetime excess absolute risk of cancer incidence per grade. And it's important to appreciate what nominal is, and this is the ICRP definition of nominal: sex averaged and age at exposure average lifetime risk estimates for a representative population. So we're aiming at this global population, if you like. But of course, these nominal risk estimates do not apply to individuals, as you've seen from up on the top of this slide, this averaging is taking place to get to a representative global population. But we can unpack those nominal risk estimates and look at the models that were being used by 103 to derive this system. And what I've shown here is the lifetime attributable risk, which is essentially the lifetime excess absolute risk of cancer incidence. And this is following the receipt of a uniform whole body dose of 10 milligray of low LET radiation. So every tissue and organ of the body receives 10 milligray. And what this shows is the variation with age at exposure down here, and by sex, so here's males and here's females, and a relatively minor variation by these composite populations that we're using. This is cancer incidence, but it does exclude skin and bone cancers, which were using rather crude models, might be too strong a word, in 103 that comes from publication 60. And in any event, these don't actually make very much contribution to the overall detriment. And so when we've unpacked this is actually the nominal risk coefficient for this particular exposure down here, which we've unpacked, disaggregated here. So, I mean, this is fundamental to bear in mind, really. However, again, you will remember that there were 10 specific models for cancer that were being used for 103 and this group of remaining solid cancers. But the individual cancer type models do vary, of course. And this, I'm illustrating this point by looking at lung cancer in the solid lines here and thyroid cancer, the broken lines here, and how they vary by sex as well. And this, again, is age at exposure. And again, this is a lifetime attributable risk of cancer incidence. And of course, it's quite apparent that thyroid cancer is very different from lung cancer in terms of its age at exposure. And there are differences in sex. So these are the models that have been used by ICRP for the 2007 recommendations. So in terms of medical diagnostic procedures, then of course, these involved almost always a non-uniform exposure of organs and tissues of the body. And indeed, these dose distributions, these organ tissue dose distributions can be very heterogeneous. And so you can actually calculate lifetime attributable risk for specific circumstances by using the application of organ tissue specific risk models, perhaps those that were used by ICRP getting on for 20 years ago now, and organ specific doses. And you can also, in the same way, this standard procedure that was outlined in 103, compare these lifetime attributable risks with effective doses calculated for these particular exposure circumstances, i.e. the doses to the tissues or organ. And for these specific exposure circumstances, the lifetime attributable risk of cancer incidence per effective dose can be derived to take account of sex and age exposure and indeed broad population group of the exposed individual. And this is what is being done here. This is the lifetime attributable risk of cancer incidence per effective dose. And this is for males and females and variation by age exposure. And these are the various sorts of diagnostic procedures giving different organ tissue specific doses, which the models are then applied to. The solid black the black broken line is whole body uniform dose of 10 milligray of low LET radiation, which we saw before for males and females. And you can see how the lifetime risk per unit dose, per unit effective dose, varies according to these different procedures, which is a reflection of the tissue or organ-specific doses and the risk models that apply to those particular organs and tissues. So there's as you can see, as you would expect, this variation by age and sex, and some, presumably this is related to the dose to the breast, but some of the variation can be quite extreme and in a few circumstances. So again, this is the lifetime attributable risk of cancer incidence per effective dose. So for a particular medical diagnostic procedure, for the organ and tissue dose estimates and the organ and tissue risk models, and they incorporate the sex and age exposure and to a minor extent, at least for the current system, the broad population group, these modifications enable overall lifetime cancer incidence risks to be calculated for typical groups of patients, i.e. those patients that fall into these particular categories. And you can also calculate the effective dose for these procedures in a standard way to provide approximate estimates of lifetime cancer incidence risk per unit dose for at least some particular circumstances. And from those graphs, you see that compared with adults in their 30s at exposure, for children, lifetime risk perceived are about 2 to 3 times higher. While if you go for older adults, then the risk per effective dose is about a half and then decreases with increasing age and exposure. And for females, the risk is about 1.5 to 1 3/4 higher than for males, and again, depending on the age and exposure and the particular procedure. So, the concluding remarks, so for a set of specific exposure circumstances, the best risk estimate can be obtained through use of the best available risk models with appropriate modifying factors. And if you were doing the best you can with the information that's available now, they would not be the ICRP risk models that we use for publication 103. There are better models available for the application. And hopefully they will eventually come through to the next set of recommendations as more data comes in, particularly from the bomb survivors. And the best available organ tissue doses. I mean, you can do that under particular circumstances. But do you really need that level of sophistication for routine purposes? I suspect not. And these routine risk estimates can be made for typical groups of patients, as we can see. But there, it has to be recognized, of course, that there are going to be other radiation risk modifying factors. Some of these are known, such as the way that smoking modifies cancer risk. That's not just the risk of smoking, that's the way that smoking modifies the radiation-related risk. And undoubtedly, there are unknown factors that will modify the risk. And at the moment, it would be difficult or indeed impossible, if you don't know what the factors are, to incorporate in the risk estimate. So I leave you with the central question, which is now going to be the subject of task group 128, led by Simon. Is approximate adjustment of risk estimates based on effective dose calculations sufficient for routine purposes, or is some more complex system required? And I hope that with this quick run through, at least of what was done in 103 and what might follow on from publication 103, you have some idea of what the issues are that we're going to have to address in task group 128. Thank you very much.
Thank you, Richard, very much, and thank you all for speakers. I think we had quite a range of presentations here, from sort of more individualized dosimetry through to some of the underpinning evidence in relation to cancer risk from animal studies and how they might be extrapolatable to humans, and then finally ending with the sort of the issues that might be being faced in the medical arena and some of the difficulties there might be in tailoring dose and risk estimates there. So we've got something like 15 minutes available for questions. So if anybody would like to, please come to one of the microphones. I think there's 3 in the room. So I think first I saw, is it Mark Shavers, I think, to the left?
Yes, sir. Thank you. This may be construed as a NASA-centric response rather than a question, but I just want to say I'm encouraged to see the LAR used as a metric in addition to effective dose. I think NASA has been addressing this for over 10 years now, since they adopted the READ, or risk of exposure-induced death, and cancer incidence limit. 2 years ago, they replaced that risk limit, which is very useful for risk balancing against other dangers that astronauts are exposed to during their mission, with effective dose. So for 2 years now, the NASA limit has been effective dose. I think that some of the comments I have are that READ has perhaps less age dependency than LAR due to competing factors. And the application of effective dose as a radiation protection quantity is useful the way NASA does it, because they do have a tie-in to risk. It's set at, for a 35-year-old female, 3% risk of exposure-induced death at the mean of a probabilistic or uncertain distribution. So that ties the risk and effective dose. So it's age and sex dependent. Smoking is not part of the effective dose, but smoking is a cofactor for risk assessment for the astronauts. So I think all of these things are relevant to your task group.
Anybody like to comment on, I suppose one of the points was use of different risk metrics for this sort of thing, and their sort of pros and cons, LAR versus REAC. I don't know. No? Okay, well, we do have plenty more questions. Anyway, so I think we'll go to the other microphone for next question.
Okay, thank you. So I have a question for Colin. So you made a clear case for that there will be a need for a more individualized risk-related quantity. And you showed it for medical exposures, so for the CT, because of course the doses are higher, and then there's progress. There's a lot of progress in how to calculate the doses for each individual. But you also said that for workers, it's not so easy to, or there's not so much possibility to get the individualized dose, but also there is progress. And for sure, at some point in time, it will be much easier and will be much better, like with all the computational techniques, to also get the doses for workers more individualized, taking in the stature and the age and all these things. So my question is, if you are thinking about this new quantity or way forward, would it not be a good idea to also include already the workers, or would you really want to limit to the medical exposures only?
Sorry, it's on. Yeah, I mean, we're not excluding other things. What we want to look at is really what are there other occupations, are there other circumstances where it would be appropriate to apply a person or individual specific dosimetry quantity. So in medicine, there's been more of a call for that, and it covers a sort of wide range and some of the larger exposures that we had from artificial sources. But we're not excluding other things, and we particularly want to go through other occupational or public exposure situations where it might be appropriate, and decide whether or not it would be appropriate for that.
Okay, thank you very much. We've got a further question over on the left-hand side. I'd like to invite Christian Streffer, please, first, who's currently sitting down, but he'll be able to get up, I think, to use the microphone. Or maybe somebody could, yeah, thank you.
You allow me to? Well, I would like to say effective dose was meant only for keeping those limits at working places. And there we have fixed parameters for the different organs. Of course, it's very tempting to use this system if you have specific groups of people, age dependence, and so on. But this was not meant by effective dose. You have to do it then with these specific parameters, and it is not effective dose. Effective dose is defined with these parameters. It is just to have an oversight on a working place situation and nothing else. And I would like to stress, if you have specific situations, specific groups, or even individuals, you should not talk about effective dose, but you should use specific parameters, and you then have a dose which gives you the risk for this specific person or group. So as one of the authors of ICRP 107, 1907, I would like to stress this. And this is not only in the last general recommendations of ICRP, it's from the beginning of effective dose, which was in ICRP 26, from the year 1967. One should always keep that in mind. These are specific parameters, and they are only should used for controlling those limits at a working place.
Okay, thank you very much for that comment. I think that I don't know if anybody wants to react to that, Colin.
Yeah, I mean, we have realized that for years and years, but people in the medical community are looking to have some sort of thing which is related to risk. That effective dose is the only thing that is available. So they have gone on and used it for all different applications, which we've not really supported, but we've not, I mean, we've stressed that it should never be used for an individual. But if you calculate effective dose for a reference phantom, as in sort of John and Richard's presentation, it does give an indication of differences in the level of risk. As it's the only thing we got, we use it. But I admit lots and lots of people have used it to many more decimal places than it should ever be used, and in different ways from it to ever be used. But if ICRP don't provide the lead in providing something, then this is what is going to happen.
Thank you. And I think there were some more questions over on that side of the room. We've got another 5 minutes or so, for sure.
Thank you for the presentation. I am a medical physicist, and in the routine work, we don't use individualization yet. So in the last presentation, you talk about routine purposes, and what are they, and what is the path to create them?
So I think the question related to the use of, well, the application.
Yeah, the use of the individualization in the routine in medical imaging.
In medical imaging, yeah.
I think, I mean, we've got a whole task group to discuss this now, but I think what all this is a requirement to strike a balance in terms of, yeah, you know, you can with the best information you have available under particular circumstances, and I can think that if it was a legal compensation case, for example, you would use the best available risk models and the best available organ doses under those calculations and under those circumstances. But you really wouldn't do that under routine circumstances. But as I understand it, you know, and Colin knows better than I about this, but effective dose is used in the medical community, and it comes out of a particular CT scan. So how are you to actually interpret that? There are ways to do it, which we've examined in publication 147. But it can only be approximate. Perhaps that's all you need, because it won't take into account, as I say, on a routine basis, every factor. It will take into account, you know, those modifying factors that are used that underlie the risk models that are used in ICRP 103. And you can then modify the risks in terms of the lifetime attributable risk per effective dose in the way that those graphs illustrate. But the patients or the individuals can only fall into certain categories and bins to be applied there. But under routine circumstances, perhaps you don't need to go any further than that. And I would say to Christian, but of course, public exposures are also expressed, dose limits are also expressed in terms of effective dose, the 1 millisievert. So I'm not expecting you to get up again. But it is the thing is whatever ICRP has said in the past, we have a current situation where effective doses are bandied about, whatever. So given those circumstances, what is the best that we can make of those circumstances? And I think that that's what's going to be the principal concern of Task Group 128.
Oh, I think a microphone's coming your way, so hang on one sec.
You certainly can calculate risk, cancer risk, with different situations, but then it's not effective dose. Effective dose is defined in ICRP 2007 with definite parameters. And it should be used, as I said, in working place, always in a low dose region.
Yeah, for sure. Yeah.
Of course, you can calculate the risk. That's fine. And you can use then specific situations. But you should not use this in connection with the term effective dose.
Yeah. Okay, thank you very much. Was there, I thought there was another person wanting to ask a question over on the left, but maybe not. Maybe the desire for lunch is overtaken. So would you like to kind of round off?
So thank you for the very active discussion, and we'd like to finalize this parallel session. Thank you very much.